Welcome. In this video I'll introduce the large aspect ratio approximation for the Grad-Strofanov equation, and this is a reason to introduce the toroidal coordinate system and learn about how to transform between coordinate systems. We'll go through the first step of the aspect ratio expansion, which is the sort of ends up with a cylindrical approximation, and then show how that relates to the cylinder solutions we found before, for when you're looking at Jacobs-Beers grad P solutions in Z pinches and theta pinches. And so this hopefully will be a bit of practice in manipulating the Grad-Strofanov equation, and then it links to the next video, which will be on the first order expansion, which is essentially the tokamak in large aspect ratios. So we start with the Grad-Strofanov equation, where here psi is some function of r and z, typically in toroidal coordinates. And so, well, it's in toroidal machine, but we have cylindrical coordinates, we have a major radius, we have a height, and we have a toroidal angle. Here we have P, a pressure, which is a function of psi, and we have F, which is a function of psi, which is the major radius times the toroidal field. And these are both flux functions because they're just a function of psi. And what we're going to do this time is look at solutions to this in large aspect ratio, which is where if you have the axis of the machine like this, so Z is up, major radius is outwards, and major radius is out like this is R, and now we have a tokamak which is a very large aspect ratio, so that means it has a diameter here, that's called A, so from the axis to the edge, which is small compared to this distance here, so this major radius is r naught. And aspect ratio is r naught over A, and we're assuming that this is large, and so often you see is people write this as an inverse aspect ratio, so you can define a small number as A over r naught as the inverse aspect ratio, and they're assuming that this is small. In real machines this is not very small, so this might be this aspect ratio might be 2 or 3, for example. So this is not typically a very small number, but the large aspect ratio approximation is still a useful one, particularly for just understanding what happens in tokamaks. So here we're assuming essentially a circular cross section, relatively small minor radius. This minor radius A compared to the major radius, which is r naught. And what this means in practice is that the variation in quantities, so we'll see shortly the things like the flux surface shape between the inside, this is the inboard, and this is the outboard. So the difference between these two is small because it's almost a cylinder. So if we made this major radius infinity, we'd just stretch out the tokamak, the toroidal system into a cylinder. And so we expect the variation in all quantities to be small around this surface. And so in this video we'll go through essentially the zero order one, where we assume that everything is constant. But first we need to transform into this coordinate system. So we have a major radius r naught, we have a minor radius, which is this r. So r is the distance or the location from the axis here to the edge, which is at r equals A. And we transform into a coordinate system where we have the major radius is r naught plus r cos theta. So theta is the angle here. So it's the angle between the horizontal and the r vector. And of course z is just r times sine theta. So we're transforming from r and z, so capital R and capital Z, into little r and theta. This is the toroidal coordinate system, which in total is sort of r, theta, and phi. So we have minor radius, poloidal angle, and toroidal angle. And here, because we're looking at quantities which are actually symmetric, so we're looking at equilibrium solutions which are constant in toroidal angle phi. So we can use this to essentially rewrite the Grad-Strofanov equation, and so let's do that. So the first term just becomes, we have a d2 psi by dr squared term, and then because we have a 1 over r inside, we end up with a minus 1 over r d psi by dr. The second term is just unchanged, so we keep the d2 psi by dz squared, and we have the same terms here, so we have mu naught r squared. We're going to call this p prime, so this is dp by d psi, minus f prime, where this is the same, this is dp by d psi, and that's df by d psi. Okay, so now we can group these terms together, so this term plus that term, this is just the Laplacian in 2D, so this is and so we can just change this to write this in polar coordinates, which is r and phi. Yes, that's transforming these two from, you can treat this as sort of x and y, ends up being the same. So we transformed from r and z into polar coordinates. This term here, we need to do a bit more work to transform. So we have so we need to know what d psi by dr is. And this essentially is just done by chain rule. So you just say that psi is a function of r and, as a little r and theta. So this is d psi by dr. So you just use the chain rule like this. From the definition of the coordinate system like this, we can rearrange this equation to work out what r is and what theta are. And so we just write down that r is just r naught, r minus r naught all squared, plus z squared. And that of course just gives r squared. And this just gives it that dr by d capital R, so you differentiate both sides here with respect to r, is just cos theta. In the same way you can write down that tan theta is just from taking the ratio of the equations for z and for r. This is just r minus r naught. And so we end up with d theta by dr is just minus sine theta over little r. And so he substitutes this expression into here, this expression into there, and then this gives us an expression for d psi by d capital R, which then goes into here. And so if you put all this together, we have the polar Laplacian for these two terms. We have these terms we just derived for this, and then the right hand side so far is unchanged. And so we now have the Grashofanov equation in toroidal coordinates. And so far it doesn't seem to be getting much simpler, but it will simplify very shortly, so some of these terms will start to remove. In particular, I want to start by looking at the cylindrical approximation, so large aspect ratio. What we're going to assume is that the solution is almost constant. So psi is, which in general is some function of r and theta, is approximately some psi naught, which is only a function of r, plus psi 1, which is a function of r and theta. And we're going to assume that this correction is much smaller than this term here. So psi naught is the dominant term, which is only a function of r. Then we can do an expansion in different in higher order corrections. And so we start by substitute this into Grashofanov equation. And so all the terms with d by d thetas go to 0. We'll end up with this term goes 0, that term goes 0. This term we'll discuss very shortly, but the main terms you end up with are, and now this term here involving a cos theta, and 1 over major radius. So we're assuming that this major radius is large, and these variations with cos theta are small, as this term is small. It implies that there is a correction to this equation, which depends on something like cos theta. So if we want to substitute in a correction term of psi 1, if you put in a psi 1 which depends like cos theta, you see this term will end up coupling to it. And so this is essentially coupling between the low order term and the higher order terms. And so we can eventually find an expansion and find this higher order correction, which we'll do in a future video. So for now, what we've arrived at is that the lowest order correction, so this corresponds to the solution in a cylinder, because we've assumed essentially an infinite aspect ratio. And so we can transform this equation into something maybe a bit more familiar. If we realize that in a cylinder, the poloidal field, so the field around a cylinder, kind of cylindrical solution, we have the fields around here, which is this b theta, and in a cylinder this is kind of the axis down the axis of the machine. So everything is constant this way. So this would be essentially toroidal angle in this way, and of course minor radius r out this way. So the poloidal field is just 1 over r naught, because we're in a cylinder, times d psi by dr. And here we're just dealing with psi naught. And in the same way, we can just write that the flux function f is just the large aspect ratio major radius times the field down the axis. And so we substitute these into this equation here, and so immediately you can see that this term here would go into there. So d psi naught by dr gives you a b theta, and this would then expand outwards and you'd get a 1 over r naught just coming through all these derivatives here. And so on the left hand side you end up with, so you have a b theta coming from here, you then have a derivative, so you end up with a db theta by dr here, or if you differentiate this r, you end up with a b theta coming out the outside. So on the other side we have terms, I realised, sorry, I forgot an r squared should be in these equations here, so there's mu naught r squared appears in here. So there should be a correction up here as well. There's an r squared here, so this follows through, we have an r squared in here, and of course an r squared in here. Okay, so this ends up, we have a minus mu naught r squared, so this is p prime is dp by dr, so p prime is dp by d psi, and this we just write as dp by dr, and then dr by d psi, because p is only a function of psi, and p here is only therefore a function of r. And so you can replace this, and you also have a minus mu naught f, which is this r naught p phi, and then for the same reason you can just replace this with a df by dr, so that times dr by d psi, and dr by d psi, this is just 1 over b theta times r naught. And so now we have a 1 over b theta r naught going into here. So both these terms have a 1 over b theta r naught. We transformed the derivatives in psi into derivatives in r. And so we multiply both sides of the equations by b theta r naught. So we multiply both sides of the equations by b theta, and then we divide both sides of the equations by r naught. And so what we have is, we end up with a b theta squared here over r, b theta squared over r, so that's coming from here, and then multiplying through by this b theta. And we have a b theta, so it's come from this term here. So this has come from this derivative with r, We've multiplied through by b theta and divided by r squared. And now here we have an f which contains an r naught, and a df by dr which contains another r naught, and so those r naughts cancel, and all that's left is the b phi. So we have a b phi times a db phi by dr, which is left over from here. And that's it. So we can manipulate this a little bit, so you can take this term here, and that becomes, of course, d by dr of b theta squared over 2. And the same here, this is d by dr of b phi squared over 2. And so now we can group together the differentials in R. So we have magnetic fields, we have pressures here. And so we have an equation. And that's the same equation we derived in previous lectures for the force balance in a cylinder. Where here we have the magnetic pressure and you have the magnetic curvature term. And you see that the pressure term came from a combination of this F term in the Grashofanov equation with this term here from the toroidal field. So in a tokamak, it's this combination of toroidal field and toroidal field, which gives the magnetic pressure. And here you have the same pressure term coming here from as you would in a cylinder. Okay, so in the next video, we'll go through the next order and show how corrections to the Grashofanov equation arise.